Hey folks, all right, I got another example of using Gauss's law to calculate an electric field created by a charge distribution. And this distribution is going to be a long line of charge. So imagine you had something like a wire or even a meter stick and you charged it up. So let's say here is your meter stick, or let's say it's a long line, okay, like a wire. So here's the wire, all right, and I'll give it a little bit of a dimension. And we want to know what's the electric field some relatively small distance from the wire. Okay. Now, what's going to happen is you're going to have electric field lines emanating radially outward from the wire. And we're going to say we're going to put ourselves close to the wire. So the field, will kind of point like if I kind of draw it in like a 3D kind of view, it's going to be kind of like that. Okay. That's all in a single plane there. So there's going to be an outward field. And what is the electric field created by that line of charge? Okay, well, let's go ahead and write out Gauss's law, double integral of E dot dA equals Qn over epsilon naught. All right, now for this line of charge, we're going to say that it has a charge density lambda. So that would be like the amount of charge per meter. So maybe you have like 10 nanocoulombs per meter on your wire. Okay. So we're going to write the electric field in terms of that lambda. So we want to avoid integrating if we can. So we want to do E times some area. Okay. What area should we pick here? What would be a good Gaussian surface? Now remember the properties of a Gaussian surface. We want the surface to be perpendicular to the field at all points, okay? And we want the field strength to be 0 or constant along that surface. Now, in the previous examples, we've had spherically symmetric charges. We've had point charges and a ball of charge, and our surface we picked was a sphere. Well, this time we don't have a ball of charge or a point charge. We have a line of charge. What surface can I surround this line of charge with such that the field strength is the same everywhere along that surface? Well, it turns out that what you're going to use is you're going to use a cylinder, like a garbage can, that is concentric with this line of charge, like so. And if you imagine the electric field lines are going to leave this surface like so, okay, and everywhere the field is going to be perpendicular to that surface, except for the top and bottom surfaces. If you imagine a field line like that, okay, that field line is running parallel to the surface or perpendicular to the surface vector. So when we do our area here, we're going to ignore the top and bottom of the garbage can. We're only going to look at the lateral area. That's the area of this surface there. What is the lateral area of a cylinder? Well, it is 2 pi r. That's the circumference. That's this dimension there times the height of the garbage can. So we're going to give the garbage can a height h. Okay. This is going to equal Qn over epsilon naught. Well, how much charge, in terms of lambda, how much charge did we capture inside of our garbage can? Okay, well, we know that lambda equals Q over L. Okay, well, what's the length of the wire that's inside the garbage can? Well, L is simply H. It's the height of our garbage can. That's how much of this wire is inside of that garbage can. So lambda is equal to Qn over H, or Qn is going to equal lambda times H. So you get E times 2 pi r H equals lambda times H, that's our Qn, divided by epsilon naught. Good news, the H cancels. Okay, it doesn't matter how tall your garbage can is. And you get the following. You get E equals lambda over 2 pi epsilon naught r. Okay, and if you do the substitution where k is 1 over 4 pi epsilon naught, you get the following. You get 2 k lambda over r. Okay, so that is the electric field strength if you are outside of a long line of charge. Now, a couple of quick notes. If you were to graph this, okay, the electric field strength versus radius, let's say this is the radius of our wire itself. So this little thing right there, that would be the radius of the wire. Well, if we're outside the wire, you get an electric field that's an inverse. It's the 2k lambda over r. What if you dig inside the wire? Well, that'll be the next video. We're going to look at a cylinder that's charged up. Okay, so we're going to leave this part for now alone. So again, we wanted to search for a Gaussian surface that enclosed part of our wire, and the field was the same direction and strength along all parts of that surface. One final note, this equation, Gauss's law, only works if you're relatively close to that cylinder. If you're far away, if you're relatively close to the wire. If you're far away from the wire, this breaks down. In other words, the wire is relatively short. Like for instance, this equation would work well if this is your wire and this is your point. Okay, this equation would not work well if this is your wire and this is your point. Okay, so Gauss's law only works well, or is only convenient, if you have symmetry, if you're close to the long line of charge. Now, something else I'll make a mention of. In the previous chapter, we derived this equation, and I'm going to see if I can find that for you. Okay, we derived that equation, so let's see, way over here. We did a long line of charge. Okay, here's what we did. We found E perpendicular for this line of charge, for this finite line of charge, and then we got an answer. Okay, so we got, this was E perpendicular, and we ended up with, let's see if we did that. Oh, I didn't actually do that. So let me talk about this. So here's E perpendicular, right? What if I make this line of charge really long? So I want you to imagine that this line of charge is really long. Well, theta 1 would be negative 90 degrees approximately if this line went off for a long way. And if this half the line went off for a long way, theta 2 would be positive 90 degrees. If we plug those in here, sine of theta 2, that would be sine of 90, that would be 1. And then if theta 1 was negative 90, we'd have minus negative 1. So we'd have 1 minus negative 1, which is 2. And you'd get your 2k lambda over how far you are from the wire D. Notice how much effort this took, though, to get to that result. That would be a lot of work, right? Well, now if we look at Gauss's law, we were able to do that amount of work. Sorry about this scrolling here, but we were able to do that whole problem in what amounts to basically 3 quick lines of work. So you might wonder, well, why do we teach you all this crazy stuff if we can just use Gauss's law? Well, here's the deal. Like we just said a moment ago, Gauss's law only works well if you have a situation where you're very close to the wire, or the wire is very, very long. So this equation only holds true if you're close to the wire. Whereas this equation is true for any length of wire, no matter how far you are from it. So this general idea of using k dq over r squared r hat, this always works in every situation. Whereas Gauss's law is only convenient to use in certain situations. So that's why we taught you all that crazy math. I'm going to do another example with you in a couple of videos from now, where the math was even crazier in the first part, but now it's going to be pretty easy with Gauss's law. So I hope that video was helpful, and thank you very much.